So our goal for today is to prove the Erdős theorem using shifting. Let us just recap some basic notions. So we work with collections of k-element sets that lie inside the first n integers, positive integers. So F we will call a family, and this notation n in square brackets choose k is just all k subsets of n, where n is 1 through n. And we say that F is intersecting if any two sets from F have non-empty intersection. In these terms, the Erdős theorem states the following thing. If n is at least 2k and f lying inside n choose k is intersecting, then the cardinality of f is at most n minus 1 choose k minus 1. So let us make two comments here. First of all, if n is smaller than 2k, then the whole collection, so the whole collection of subsets of size k in the first n elements is intersecting. So this thing itself is intersecting, just because you cannot fit two sets of size k inside n. So this is the first comment. So this restriction is only natural. And the second comment is that this thing is the size of a trivial family, which is the sets of size k that contain 1. So this is probably the most natural intersecting family. The intersection is witnessed by the first element, and it turns out that this is just the best we can do, the largest we can do in this respect. So how do we prove it? We'll need some preliminary notation related to shifting, since I promised to prove using shifting. So we'll do it briefly. I'm not going to verify the properties related to shifting. I'll just state that the first step of the proof is reduce to the case when f is shifted. So let us here give the necessary definition. F in n choose k is shifted if whenever a set A is in F, where I'm writing A as a kind of ordered tuple because I mean that A1 is smaller than A2, smaller than AK. So whenever F contains this A, and we have B such that BI are smaller than AI for every I, then B also belongs to F. So, in words, if you have a set in F and then you replace some of its elements by some smaller elements, then the resulting set is also in F. So the first step of the proof is to reduce the problem to the case when F is shifted. This is done roughly as follows. You introduce like more fine-grained operation called an ij shift when you replace an element j by an element I whenever possible, and then you show that when you do these shifts, the family, or you apply these shifts to a family, first of all, the size of the family doesn't change, and second, if the family was intersecting, it stays intersecting. So this you can see in one of Julius Kaplan's videos that also gives a proof of the Erdős theorem. And then basically you repeat these shifts, and eventually you reduce any family to a shifted family while preserving the intersection property. So this is the reason I avoid it is because it's somewhat technical and thus not very interesting to show in a video, in a short video. So in the natural second step is just prove the theorem for shifted families. And this is what we're going to focus on today. So how are we going to do this? We split F into two parts based on whether a set from F contains or doesn't contain the last element of the ground set. Let me define these things. This is the collection of sets from F that contain n with n removed. And this is the collection of sets that doesn't contain n. So this is the split that we are going to work with, and the proof is going to be by induction. So the base cases are k equals 1 and n equals 2k. For k equals 1, the theorem says that if you have a collection of singletons that is intersecting, then you can have at most one singleton, which is trivial. And for n equals 2k, it's a little bit more work, but not much more. So this is trivial. And this is as follows. The bound says that the cardinality of F is at most 2k minus 1, choose k minus 1, which is equal to 1/2 2k, choose k. So the bound says that we have at most half of all the sets of size k, and we simply say that we can split all sets in complementary pairs and we can take at most one from each pair. Thus at most half from all the sets. So this is the base, and the more interesting part is of course the induction transition, and here we are going to use the induction assumption for the pairs n-1 k-1 and n-1 k to go to n k. So let us take a look at the split that we wrote above. So this family is intersecting. Out of the two families on the right, this one is clearly intersecting, just because it's a subfamily of F. And thus we can apply induction hypothesis to it. But as for the first family, it is unclear. And this is, like, a priori for an arbitrary F, it's not true that this would be intersecting, because, well, we may have two sets that intersect exactly in n, and thus once we remove n, the resulting sets do not intersect, but this is where we will use shifted. And this part goes as follows. So the key claim f of n is intersecting. So why is it true? Well, assume not. Then there exist A, B, two sets from the original family such that A intersection B is equal to n. So what we do is we take two sets from f of n, they're disjoint, since f of n is not intersecting, and we add back n, and we get two sets from the original family. Now n is bigger than 2k, and thus there exists a certain element x from the following set: n-1, the first n-1 integer, minus A union B. So note that this thing has 2k minus 2 elements in n-1. So clearly there is room for x. There exists such an x, and by shiftedness the set C, which is B minus n union x, is in F. So the set C is in F simply because we can obtain it from B by replacing N with X. And C intersection A is empty, which is a contradiction to the property of F being intersecting. So the rest of the proof is a pleasant and easy calculation. So what do we have? We have the cardinality of F is equal to the cardinality of F of N plus F of bar N. Now let's think for a second. So looking at the definitions, both families live on the first n minus 1 integers. The first family is of sets of size k minus 1, and then the second family is sets of size k. Now we can apply induction hypothesis to both, since both are intersecting, and thus this is at most n minus 2 choose k minus 2 plus n minus 2 choose k minus 1, which together gives us n minus 1 choose k minus 1. That's the end of the proof.